Hello everyone and welcome back. This is lecture 5. We are going to finish chapter 3. We are at the very end of chapter 3 and we are going to conclude this chapter with the last two books or few books of elements. So last time we talked about number theoretical parts of elements, and this was discussed in the last few books, starting with book 7 and so on. And then book 8 and 9 deals with the concept of incommensurable quantity, or what we know them to be irrational numbers. Book 10 was also dwelling more on this concept of irrationality, and by the standard of most historians of math is known to be the most difficult book. However, book 11, 12 and 13 deal with solid geometry. That means the three-dimensional geometry. So the very last book culminates with the proof that there are only 5 regular solids, or otherwise known as Platonic solids. So that's the very last proposition, proposition 465 of the book, and that ends the elements. So before I actually talk about these Platonic solids, I will define a couple of things, and then we shall explore one by one what these solids are. Okay, so the very first thing we mention or define are the polygons and then regular polygons. So what is a polygon? A polygon is a two-dimensional shape, closed shaped, made of straight lines. So I'll just write this definition. A polygon is a two-dimensional shape made of straight edges or straight lines. So what would be the smallest, or the smallest example that we know? That would be actually what? A triangle. You need at least 3 straight lines to enclose a shape in a two-dimensional space. So before I move on, polygons come in 2 flavors, convex or not. So what would be a convex polygon? A convex polygon would be a polygon that it has no dents in it. This is a very loose definition, of course, but I'll just write an example. We don't need to know the formal definition for this for the moment. So here's an example of a non-convex polygon. Okay, so so here's the dent, but to just say a dent is certainly not good, not in mathematics anyway. One way you can think about non-convex polygons is as follows. If you can connect any two corners, any 2 vertices of this polygon with a line, and that line falls within the area of the polygon, then your polygon is convex. But if you can connect any 2 vertices of the polygon and the line that connects them falls outside the area of the polygon, in that case the polygon would be non-convex. Here's an example. If you connect these 2 vertices, the line that connects them definitely falls outside the area of the polygon, so this would be an example of non-convex polygon. A convex polygon will look something like this. So if you were to connect any two vertices of this polygon, I don't mean any two vertices, I mean any two vertices that are not adjacent to each other, because if they are, then that's one of your sides of the polygon. For example, if you want to connect these two, the line falls within the area. If you want to connect these two, the line falls within the area. The same thing with this two, and the same thing with this two. So here's an example of a convex polygon. So this concept of convexity sort of plays a role in what comes a little later in this lecture. So let's move on again with polygons. What do we mean by a regular polygon? I define here what a polygon is. A regular polygon would be, again, a two-dimensional closed shape made of straight lines. I should say here a closed shape, two-dimensional closed shape here. Let me make that distinction. So a regular polygon would be a two-dimensional closed shape made of straight lines, such that all these straight lines are equal to one another and all the interior angles will be equal to one another. So is there a familiar regular polygon that we all know? Sure, that would be the square. All sides of the square are equal to one another, and all the interior angles of the square are equal to one another. However, a triangle is a smaller regular polygon that we know. In fact, we do know of triangles such that all the sides are equal to one another. So regular polygons is a closed two-dimensional shape made of congruent straight lines or equal straight lines. Congruent straight lines. Okay, so equilateral triangles would be the very first such regular polygon. So I'm just going to try to draw some loosely. So that's a triangle, and the next thing we know would be a square. All sides of the square are equal to one another, and all interior angles are equal to one another. The next shape after the square is the so-called pentagon, is made of 5 congruent or equal sides, and it looks something like this. I should start here perhaps. It looks something like this. And then the next shape would be one with 6 sides, and that is called the hexagon, and it looks something like this. And so on. In fact, for every natural number n, there exists a regular polygon with that many sides. So let me just say here, for every natural number n, there exists a n-gon, a regular n-gon. So the larger the n becomes, the more and more the shape would look like what? Like a circle. So as n goes to infinity, meaning as n becomes larger and larger, the regular polygon looks like a circle. Sometimes the circle is referred to as the infinitagon. Okay, well, the question is, we're not really that interested in polygons or two-dimensional shapes as far as this lecture is concerned, but we want to ask the question, could we build a regular solid? What does that mean? Could we build a three-dimensional closed shape such that all of its faces are regular polygons? That is actually the definition of what a regular solid would be. Solid, I mean a three-dimensional closed shape. And could we build some? Yes, we could. But much like the polygons, is it possible to actually build infinitely many such regular solids? Or somehow in a three-dimensional space we might be limited? And the answer is no. No, in the sense that no, we cannot build in 3 dimensions as many regular solids as we want. Now, in 3-dimensional space, surely there are lots and lots of polygons, not polygons, I'm sorry. In 3-dimensional space, we call them polyhedron or polyhedra for many of those. So, polyhedra, there are many irregular polyhedra, but not regular ones. In fact, the great theorem of this lecture, if you will, is the following. There are only 5 regular solids. What would be a non-regular solid? So an example that might come to mind is a pyramid, for example. As you know, the pyramid, it has a square base and all the other faces are all triangles, but the base is not a triangle. So yes, it is a solid, but not a regular solid. So let me just move on here and I'll write what do I mean once again by regular solids, and then we'll talk about some of those. So regular solids. So a regular solid is a convex. It is a convex 3-dimensional shape. Notice here in the definition this concept of convexity, because everything that we will be talking from this point on is true and valid for convex regular solids, so or convex solids. A non-convex solid would be any solid that has a hole or a dent through them. It's certainly difficult to draw, so I'm not going to draw those, but I am going to give examples or drawings of the regular solids. So let me just move on with the definition. A regular solid is convex 3-dimensional shape with congruent or equal with congruent faces as regular polygons. So it would be a 3-dimensional shape, closed, and faces of this shape should all be regular polygons of the same kind. So again, what would be one very familiar regular solid that we know? That would be the cube. If you know, the cube, all the faces of the cube look the same. They are all squares, and from every vertex or every corner, the cube looks very, very much the same. So it has a lot of symmetry. However, cube is not the very first solid, but the very first regular solid that we know is the so-called tetrahedron. Tetrahedron is made of, I'll give you a picture. Okay, let me just write it here first and then I'll show you the picture. So the very first one is the so-called tetrahedron. Tetrahedron is made of 3 regular triangles. So it has, I'm sorry, not 3 but 4. It is made of 4 regular triangles, 3 on the top and 1 on the bottom. So it has 4 faces, and they are triangles. The next one would be cube. Cube sometimes is known as hexahedron because it has 6 faces. So this polyhedra are named by the number of faces. Since cube has 6 faces, is otherwise known as hexahedron. It has 6 faces, so the faces all look like squares. The next one would be the so-called octahedron, is made of 8 triangles, hence octahedron. It is made of 8 faces, and they are all triangles. The next one would be dodecahedron. It is a regular solid that is made of 12 faces, and these are nothing other than pentagons. So the faces of dodecahedron are all pentagons. And the last one is icosahedron. Is made of 20 faces, and they are all triangles. Okay, what do they look like? They look like this. This is the tetrahedron, is made of 4 faces. If you were to open this up and lay it flat in 2 dimensions, you'll see that the tetrahedron is made of these 4 triangles. 1, 2, 3, 4 triangles. If you put them up in 3D, you'll come up with the so-called tetrahedron. Cube, as you know, is made of 6 squares. 1, 2, 3, 4, 5, and 6. If you put them together, you get cube. Octahedron, as I said before, is made of 8 faces, and each of them is a triangle. So 1, 2, 3, 4, 5, 6, 7, and 8. If you put them together, you'll get the diamond shape. Dodecahedron, it has 12 pentagons as faces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Put together, you get this shape. And icosahedron, it has 20, is made of 20 equilateral triangles. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So if you lay them flat, it's nothing other than a bunch of regular polygons put together. And here is a bit more transparent picture of those 6 solids. So I'll refer back to this again. So as I said before, question is, could you build much like in the two-dimensional space? Is there a regular solid for every regular polygon that you can build? As I said before, the answer is no. And the big deal is to prove that there are only 5 and no more. Now, geometers of the time, Euclid's time, knew that these 5 solids did exist. And it was not until Euclid, or he is the one who actually proved that there are only 5 such regular convex polygons, no more, no less. How did he prove it? Well, he proved it by using the fact that he had proved before in a book or two before, that the sum of angles, solid angles, meaning the concept of an angle in three-dimensional space, the sum of angles or solid angles in a regular solid, it cannot be more than 360. So that's a proposition that Euclid proved in one of his books, and he used that fact to prove that there are only 5 regular solids and no more. We are going to actually follow a different approach. It's not in the book, so still is very, very interesting. So before, and simple too, not a difficult proof. So before we get there, let us fill this table with numbers that have to do with this 5 polyhedra, and see what are some of the relationships between these shapes. All right, so some notations. So here I'm going to, that's the polyhedra. Now, big V stands for the vertices of a solid, so, or the corners of the solid, vertices. The capital E stands for edges or sides of a face of a polygon. F stands for faces of a polygon. Okay, so here I will have the number for faces, here I will have the number for vertices, here I will have the number for edges, and this will be for tetrahedron, that would be for the cube, I mean this row. This would be for octahedron, this will be for dodecahedron, and that would be for icosahedron. Okay. Now, a little bit more notation. With letter S, small s, would be will be denoting the number of sides, so that would be the number of sides on each face, on each face for each of these. So let me, here would be S. Little c would be the number of sides that comes out of each vertex. We shall try to count those. So c would be the number of sides coming out of each vertex, Okay, so here I will write the numbers for C, and here we'll write something else when the time comes. So let's see if we can count. I'm bringing back the tetrahedron. All right, so number of faces. This is not so difficult. Tetrahedron, as I said before, has 4 faces. 1 on the back, this one here 3, and the bottom 4. So it has 4 faces, just said before. Cube has 6 faces. Octahedron has 8 faces. Dodecahedron has 12 faces, and icosahedron has 20 faces. All right, let's try to number the vertices. Again, for tetrahedron is not so difficult. There are only 4 of those. 1 vertex, 2, 3, 4. So there are only 4 vertices for tetrahedron. How about the number of edges? Well, that's not so difficult either. So let's see. 1, 2, 3, 4, 5, 6. There are 6 edges. Let's see how many sides each face has. Since each face is made of triangles, then each face will have 3 sides. What would be the number of sides emanating or coming out from each vertex? Well, since all sides are, all faces are triangles, when they meet from each corner or each vertex, you'll have emanating only 3 sides. So this is only 3 as well. Okay, moving on to the cube. This is also familiar and not so difficult to count. So how many vertices the cube has? 1, 2, 3, 4. 4 on the top, 4 on the bottom. That is 8. Number of edges. Well, how many edges? You do have to be a little careful. You can count them and you can say, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 edges. Not so bad. The number of sides on each face, since they are all squares, obviously would be 4. What is the number of sides coming out of each corner? Not 4, but is 3. Each corner you have only 3 sides emanating, so this is also 3. Okay, moving on to octahedron. I know I have 8 triangles, is made of 8 triangles. Well, let's see how many vertices there are. Not hard to count. You have 4 in the middle, 1, 2, 3, 4, and 1 top and 1 bottom, so that would be 6. Well, number of edges, let's see. You have 1, 2, 3, 4. That's half of the pyramid, if you will, or half of the octahedron, which is a pyramid. 1, 2, 3, 4. 4 on the top, and you will have 4 on the bottom. 1, 2, 3, 4 on the bottom, and 4, that is the base. So you will have 12 edges altogether. Out of each corner, if you carefully look at it, out of each corner, how many sides are emanating or coming out? 4. 1, 2, 3, 4. 1, 2, 3, 4, and so on. From each corner you have exactly the same number of sides emanating. So this is 4. I'm sorry, I made a mistake. This is 3 here, since the faces are triangles, and number of sides coming out of each vertex is 4. Okay. Well, things get a little bit more difficult, at least visual would be a little bit more difficult. I know that I have 12 pentagons here. How many vertices? Well, we can count, but should we? We can easily make a mistake. So let me see if I can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20. If you were to hold this in your hand, well, as I actually do in a regular environment in class, I usually bring all of this. If you're holding this, it's kind of hard to count them all and not make a mistake. But here I have a picture of it, so I can easily count. In any event, what about the number of edges? Well, let's see how many edges. How many edges I will have? 1. Looks like a lot. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, and I'm missing 3. 27, 28, 29, 30. So there are 30 edges. Again, kind of hard. I'm not going to bother counting here, but before I count the rest, well, here at least, I'm talking about icosahedron, but I'm still here anyway. So number of sides on each face here is 5 because we're dealing with a pentagon. And number of sides emanating out of each vertex is 3. 1, 2, 3. So that's not so hard. Now for icosahedron, probably I shouldn't bother counting. And why would I do that? Well, I'm hoping to actually come up with a formula. I'm hoping to come up with a formula that actually counts the number of vertices and edges and sides for each solid. So let's see. Let me try to come up with the formula to compute the number of edges. So I want to come up with a formula for edges. Now I know that I know the number of sides on each face. So I can take the number of faces and I can multiply it by the number of edges on each face, but that's a lot. That's a lot. For example, the tetrahedron is made of 4 faces, and each face has 3 sides. So 4 times 3 is 12. I know that tetrahedron does not have 12 edges, but it has 6. So I need to divide by 2, and then I get 6, and that would work. So I'm talking about number of faces times the number of sides on each face divided by 2. Would that work for all others? Well, let's see. Number of faces for the cube is 6. Number of sides is on each face is 4. 6 times 4 divided by 2 would be 12. So that works. Octahedron, number of faces, 8 times 3 divided by 2 would also give me 12. So that works. 12 times sides on each face, which is 5. 12 times 5 divided by 2 would give me 30. 60 divided by 2 is 30. So I can easily say, well, sides on icosahedron are, since they are triangles, they are 3. And for icosahedron, I can actually see the number of sides coming out of each vertex, which is 5. 1, 2, 3, 4, 5. From each corner of icosahedron, you have 5 edges emanating or coming out. So this is 5. So I can say 20 times 3 divided by 20 times 3 divided by 2 would be, where am I? The number of edges would be 20. And no, I'm sorry, what am I saying? 30. So if you actually count, you do have exactly 30 edges here. Why is that so? I mean, why should it work? If you notice in each shape, each side or each edge is counted twice. For example, for the cube, this particular side is counted once for this face and once for this face. Twice. The same here. This side is counted for these two faces. This side is counted twice for these two faces. This side is counted twice for these faces. This side is counted twice for these faces. And that is the case with all of them. That's why we divide them by 2, and that would be a formula that works. Is there another way to compute the number of edges? Sure. Here's another formula, and let's see why that would work. You can multiply the number of vertices by the number of sides coming out of each vertex and divide that by 2. So the total number of vertices for a regular solid times the number of sides coming out of each vertex divided by 2. Divided by 2 again, only because edges are counted twice for each face that they separate. So that also would work if you just plug in the numbers that you know. You will see that everything works out. So the number, there is only one thing that I haven't completed here. I do have, in fact, 12 vertices. Now, I'll work with these two formulas, and I'll make sure that they are incorporated in the proof that will follow. All right, notice the following. From here, from this formula, what can I say about the number of faces? Can I solve in this formula for the number of faces? The answer is yes. So from here, the number of faces is equal to what? To 2 times the number of edges divided by s the number of sides. And from this formula, here I can solve for vertices. Vertices here is equal to 2 times the number of sides divided by the number of sides that emanates from each vertex. So I shall use these two formulas shortly. Now, before I actually move on with the proof, note the following. What if I was to compute the following quantity for absolutely each of those solids? Vertices minus edges plus the number of faces. What that number would be for all these solids. So here, 4 minus 6 is minus 2, plus 4 is 2. 4 plus minus 2, or 4 minus 2 is 2. Okay, let's move to the next one. 8 minus 12 plus 6 is also 2. Next one, 6 minus 3 plus 8 is also 2. 12, not 12, what am I saying? Going back to the octahedron. 6, yeah, I was right about this. 6 minus vertices, edges. 6 minus 12 plus 8 is 2. Has nothing to do with 3 here. I got confused. All right, next one. 20 minus 30 plus 12 is also 2. 12 minus 30 plus 20 is also 2. So as you can see, this quantity turns out to be constant, namely the constant 2 for absolutely all 5 of those solids, and that would be at the heart of our proof. In fact, this relationship between vertices, edges, and faces of a regular solid was known, was discovered, and was known way before, some 4,000 years before Euler. But Euler is the one who discovered this formula or this quantity, and actually proved that this is always 2 for any, not just regular solid, but for any convex solid. This is true. This is true, and it is otherwise known as the Euler's characteristic. Okay. The concept of Euler's characteristic, it is a little bit more involved, but initially this was rediscovered and proved for convex polyhedra. They don't have to be regular or not. As long as they are convex polyhedra, then this relationship between vertices, edges, and faces is always true, meaning this quantity is always equal to 2. So Euler proved that in the 1700s, which is so much later than Euclid's time. As I mentioned at the beginning of the lecture, Euclid's proof was a little different. So this would be the end of part 1. I'll just do the proof, and that would be part 2. Be back in a minute.